All right, let's carry on with Chapter 2, which is an overview of the protocol. So, in the early days of the Internet started with only 4 servers, which were at colleges. Then it expanded to more and more, and at that time there were only a small number of domains, so they just had floppy disks that they would just deliver physically to the addresses of the few people that had them. You'd get a floppy that had the hosts file, and you'd periodically get a new floppy with the updated hosts file. There was no DNS system. You stored this information in /etc/hosts, and that was the one file that contained a list of domain names and IP addresses. And of course, that works for a small number of domains, but after a while, there were too many companies and it was changing too fast, so they created DNS in the 80s. And so the plan was to have distributed storage, so it didn't just depend on one server, so if that server was down, it wouldn't cause it to go down. And a hierarchical organization where you have layers allows you to have local control of your local machines, where you don't need to somehow send your DNS records up to some central service, which will store them for you. You can just record it on your local DNS server that's under your control, and you don't have to be more organized than that. So we had this structure. You have a host name first, then you have a domain name, which is something .edu or .com, typically, that kind of thing. And this is the top-level domain, the edu. This is called a fully qualified domain name with up to 4 labels. You can have 2 over here, and then you can have the name of the company, and then a dot, and then a top-level domain, which originally had to be drawn from a list of 7 allowed top-level domains, and now they've allowed it to open up to hundreds of them. And last week or so, Google actually added a .zip top-level domain that they're selling, which is highly controversial because people think that's a file, and it looks like a domain, and that opens a whole new world of unnecessary social engineering attacks. So plenty of people are mad at Google for that, but they did it. Anyway, so here's the hierarchical space. You have the root, which only stores where the top-level domains are, like com and net and US, and then each one of those has a list of the companies, like example.com, and each one of those points to their local name servers, which will be whatever that company chose to set up. So if you are at example.com, you have your own name server, and you can just add records to it to match all the servers and other things you have down here, and you don't have to inform anybody else. Everybody will find you, because when they're looking for something like games.example.com, they'll go ask .com where example.com is, and they'll ask your server. So they'll find their way to your server to find your machines without you having to send that data to somebody else. It's very clever that way. These things are called DNS zones. So a CCSF server would have control of the CCSF zone, and it would have all these records. It wouldn't know anything about anything. It didn't end in ccsf.edu, but it would know what its zone files are. Then you can have domain delegations. You can split your own company. You could have Ocean and Mission and Evans at different campuses, and each of these could be its own zone with its own DNS server. You're allowed to split up your own DNS into sub-DNSs if you want to, and that's what a large company might do. So your DNS client is the machine, the software on your machine that requests domain names, usually your web browser. And then you have a server somewhere which stores and serves data. And typically we go through a resolver. Your home router that you buy, your $30 router, serves as your DNS resolver. It doesn't have a database of DNS names. All it does is forward it to the ISP. It's a resolver. You ask it a question, it asks somebody else. That's all it does. But it means the address it sends to your endpoints is good enough to get a DNS reply. So DNS servers are the ones that actually have a database with all the information of all the IP addresses in a zone. And there's different kinds. The authoritative server is the one you specify as the master copy. You might have multiple name servers, and you usually do, for availability in case one is unavailable. But one of them is the master. So you put new records on the master, and the others just copy that data. That's the start of authority. Then you have caching servers that store data for a while without asking any questions, just to give faster performance. And every cached record has a time to live, which you can see. In fact, we should be able to see it here. If I do a dig of say, samsclass.info, you see this number, 1554? Now it's 1550. Now it's 1548. That's the cache. So when I queried, it found a cached record, and this is the cache counting down. It's going to last for 1,500 seconds, and when that hits 0, it will ask the server above it and get a fresh copy. That's what's going on. And you can specify on your DNS server how long you want the records to last. But typically, you let them last for at least an hour or something just for performance. Now that means if I was to move my website to a different server, some people would not be able to see it for an hour because they'd be looking at an old record that wouldn't get updated. So that's the trade-off. A longer cache means your DNS server has less traffic and people get faster response, but it also means if you do change it, there's a dead time when people are going to an old address. Yeah?
So you mean the IP address there going
to
be changed?
It might change because Cloudflare has a whole, changes it a lot. Yeah. If you only had one server, then it wouldn't change. All right, so a recursive query is the most common. This is what happens with a resolver at home. You ask your resolver at home, where is yahoo.com? It doesn't know, but it's a recursive query, which means find out, even if you have to ask somebody else. And so that's the normal. An iterative query will send the referral to another server. It's a very similar thing. All right. So a forwarder is what you have at home. That's what your router is. You send it a query, and it doesn't know, but it asks other servers, finds the answer, and tells you. So your endpoint, it feels like it knew. You asked your router told you. Your router didn't actually know anything. It had to ask somebody else, but, you know, that's not obvious. All right. So that's your resolver, queries the DNS server, and a stub resolver is something connected to only one recursive server that can't follow referrals. The Windows stub resolver caches. This is the thing, you have a cache in your Windows machine. If you go to a site like yahoo.com, if you go again to that site, it doesn't even ask the router where it is. It looks in your Windows operating system, has its own cache for about 2 minutes. So it doesn't ask again. Linux does not cache things. So if you get a bad entry in the cache, you have to clear the cache, and you can do that on Windows with ipconfig/flush DNS. So your local DNS server, if you do your ipconfig, you can see you'll have a DNS server here. If you do ipconfig/all, it'll tell you your IP address. And for most people, the DNS server is equal to their default gateway because it's just your home router. If you're at work, they might be 2 different machines. All right, so here's the typical name resolution scenario. I say, where is ccsf.edu to my local server? It then does whatever queries it has to. If it has just booted up and it doesn't even know where .com is or .edu, then it has to ask the root. Typically, it already knows that. Then it will ask this top-level server, edu, where is ccsf.edu, and then it will go to here and find a name server, and then it can ask where is www.ccsf.edu. All right, DNS replication. If you have one server, that's got the primary zone file, and now you have slave servers that just copy it. And the zone transfer is the network traffic that copies the zone information from one DNS server to another. That's how you replicate them. And by the way, there's a very similar process for Windows domain controllers. So the root server is named .dot. That has points to the top-level domains like .com and .biz. And then if you just rebooted your DNS server, then it will have to ask this because it's forgotten where .com is, but most of the time it knows that. The roots, yeah.
At home, I don't have DNS server.
Well, no, if you have a router, you have a DNS server. It serves as a resolver. Your typical router serves that purpose. But all it's doing is forwarding to your internet service provider, which provides DNS service. It's part of the service. You could, in principle, have a internet service that didn't give you DNS, but nobody would want it. All right, and so the root server just has 13 domain names in it, which are the root servers, A through M at rootservers.net. All right, and so various types of records that we talked about. These are called resource records, the kind of data in DNS. The most common one is A. It gives you an IP version 4 address. That's usually what you want. Quad A is IP version 6. Here's mail. You can have pointers, which are host names that point to another name, just sort of like aliases. Here's the DNS servers, NS. And it doesn't, not necessarily an SOA, but anyway, here's canonical name is another way to make an alias, and text is a way to make general information, and we'll play with these in the hands-on projects. Here's some more resource records types. Here's a service you can have. Here's one I mentioned before. SPF is an anti-email spam method. This limits who should be sending email from here, so you can check it. And here's the ones for DNS Sec, DNS Key, DS, RRSig, and NSEC. We'll talk about these later in the course. These are all those cryptographic things that try to add cryptographic security to DNS, which is a good thing, but it is very complicated and it's rolling out very slowly. Many people are just not bothering to upgrade because you don't really have to, and it's kind of a lot of work. So if you do a dig any of ccsf.edu, we've already done this. You see various things. Let me do it live with the Ring of Saturn. It's easier to see. Okay, if I do dig any of CCSF, I'm surprised the any's are still working. Several years ago, they were supposed to be deprecated, but these servers are still honoring it, which is handy. So any should tell me everything it knows about CCSF. And so it has a start of authority, which is ns3.ccsf.edu. It has a text record, which is a Google site verification. I think this is something you have to do for Gmail to accept your emails. You have to have this kind of thing there. Then there's another text record, something about Amazon, which I think is something they had to do to use AWS. Here's the Sender Protection Framework record in a text file. Here's some kind of Adobe thing. So a lot of companies are expecting you to have these text records. And here's IP version 4 address. Here's some name servers, more IP version 4 addresses. And so that's City College. One thing missing is IP version 6. We haven't upgraded to IP version 6. Everything is still running on IP version 4 here, which is also very common. IP version 6 and DNS Sec are improvements, but many companies haven't bothered to implement them yet because you don't really need them for most traffic. All right, and so IETF, we already did this. IETF has all the fancy stuff, all the big cryptographic records, because they're the ones that write the standards, and so they're, of course, using the latest version of everything. And there's that looking glass at Ring of Saturn that I like to use for this, for demonstrations. All right, then there's reverse DNS lookups. So if I look at this, City College has this IP address down here, this 54 thing. This is one of City College's addresses. Here's another one. I'm more familiar with this one. I'll use that. You can look for an IP address, not a domain name. That's a reverse DNS lookup. This is a public address. If you look for that, it's going to find that it came, might find that it came from ccsf.edu, but looks like I'm not finding it. Oh, that's right. I need to add something. I need to put in adder. I think I can do it in adder.arpa. I think this will do it, and then it should be backwards. 247, 144, 144, 146. I think this might work. If it doesn't work, I'll have to wait until we get to it in the project. I think this will do it. All right, we'll do it later. Anyway, you can do a reverse lookup where it looks up from an IP address to a domain name. And we're going to talk about this. This is important. It's only going to work if there's a public service with a DNS record tied to that public address. All right. So you can reverse the order. You do that, and then you look for a pointer record. So I think, in fact, I just need to do a pointer here. Let's try this, and then I'm going to quit if it doesn't work. Yeah, it didn't work. We'll do it later in the projects when I can get it right. All right. So that's a reverse DNS lookup. Here's the one I did. It was dig, -X, there. Okay, good. Thought there was an easy way to do it with dig. All right, let me try it again. So I can do dig -X for that address. -X. All right. That's going to look for who owns that public address. And it tells me it's ccsf.edu. That's what I wanted to show you. So if you have a public DNS, you can do a reverse lookup to see who owns it. And this is something you might do to make sure that email is not coming from the wrong server, so it's not spam. But it only works if that address is publicly registered somewhere. All right. There's a forward lookup for Google. Dig quad A on Google. You get an IP version 6 address. And there's a reverse lookup for Google. You can do a reverse address with the IP version 6 address, and you'll get an answer, hopefully, that tells you it has something to do with Google. Although this one didn't give me a good answer for the IP version 6 address at that time. All right. And so here's, in addition to the normal top-level domains like net and com, there's ARPA, which is the one used for reverse addresses. That's why it's ARPA and INADDR, and down here they're arranged by numbers. So this is what's actually used. There's a second database used for reverse DNS lookups, and you'll see this in the projects. We're going to set these up on your servers. All right, so here's the format of DNS packets. You have a header. Let me get rid of this unnecessary stuff here. All right, you have a header of 12 bytes, then you have a question, then you might have answers coming in, and then authority records saying where did you get that answer, and then additional records with extra information. This is the structure of a DNS packet. And the fun thing we're going to talk about more as we go ahead is this transaction ID. When you send a DNS query, there's an ID number in it, so when you get a reply, you can tell which reply is answering my question, in case there's a lot of DNS packets flying around on the network and you can't tell which one is for you. And here you get a number of questions, number of answers, and so on. We'll see this live. Here's what it looks like. You have query or response. You have queries, ask questions, responses are the answer. Then you have other things here. You read the record code and so on. There's various flags to specify these like forward or reverse DNS and recursive or iterative, different types of queries. And there are glue records, which are really, really twisted and insane. Here's a fundamental problem. If I have ccsf.edu, that's my domain, and I make my name servers like ns.ccsf.edu and ns2.ccsf.edu, well, if I don't know anything about ccsf.edu, they say, well, if you want to know, go to ns.ccsf.edu. Well, I can't find that because I don't know where ccsf.edu is. To start, I need to have an address for it that is not in the ccsf.edu domain. That's called a glue record. And this means every single website, here's the name, where is it? Well, ask the name server. Well, where's the name server? You can't find it until you know where it is. So to prevent this, you have to have a glue record in the top-level domain zone. So the .edu server has to have a hard-coded address for every domain under it. It's a huge database. It's a huge burden. And it does seem like kind of a stupid way to do it, but that's the way it is. So you can view them with dig. So let me do this live. First, I'm going to dig NS of edu. So I do dig NS of edu. All right, so here are some top-level edu servers for the edu domain name. Now, I dig NS ccsf.edu at one of them. So I dig NS ccsf.edu at one of these. I'll use this one. edusservers.net. All right, and that should show me the glue record, and there's the address. Yep, so that address is hard-coded. What I did not look at a City College server. I looked at one of the top servers for the .net domain name, and I found this address. So that's your glue record. Nobody would be able to find a new company unless you do this. If you open a new company, nobody's been there before, they're going to try to find it, and they're going to have to use this address to find it. So you have to put this glue record up there. This is a problem. A lot of DNS hosting services don't provide that glue record. You have to pick them carefully. At least they didn't used to for IP version 6. Anyway, they find glue records for various things. All right. There's also this crazy thing called a bind version query, which is sort of nuts out there. Let's see if this one still works. Dig, let's try ns1.ccsf.edu. I think ns3 is the lowest one we have. See if this still works. This is an old strange trick. Version.bind. Text chaos. Yeah, it looks like that one's being blocked these days. Anyway, this is a strange thing. You used to be able to tell what version of bind was being used. We're going to set up bind servers, and bind used to be the universal DNS server used everywhere, so you would report what version you're using all the time. This turned out to be a pretty bad idea. There's no point advertising the fact that you're using an old version of something and inviting attacks. Anyway, one of the strange things in DNS at that time. Does it need a period after the word bind? It might. Yeah. Anyway, I see some good hints up there. All right. Anyway. So ISC.org, the authors of bind, were using the latest one at that time. Anyway, it's not that important, just kind of a stunt. So we'll talk about some server architectures. So for a small company, you probably would just outsource DNS to somebody like Cloudflare, like I did. It's too much bother for me to run a server and make sure it's always up and has backups and everything. I just use a cloud service. So my company is here, and I've got my router and my endpoints, and I just have my own servers somewhere up in the cloud, hosted somewhere. All right. For a medium company, you have internal and external DNS, and we're going to set these up. You have one server, which is used by your clients to access the internet. So let me just make this bigger. So here's your internal DNS server. So when these people try to surf the internet, they go to your DNS server, and these are set up to do recursive queries, like your home router. So they will find yahoo.com and everything and help people find it. This is used for outgoing traffic. For people coming in to get to your servers, they'll use a different set of servers configured to service the address of your servers. You don't want to mix these two. You want one server for people outside your company trying to reach your company servers, and a separate servers for your internal workstations to use to find addresses on the internet. You don't want to mix those two together because they have different confidentiality requirements, which we'll talk about a lot more as we go ahead. What's that?
Can you explain this one more time?
Yeah. See, when these guys are surfing the internet, they want to have a server that has access to the whole internet. It just finds domain names and does it recursively, like your home router, which is fine. So these servers serve that purpose. But when people outside your company try to go to your company's website, you want them to find your official web services, and you have another DNS server that serves that purpose. And this one is an authoritative server, and it is not recursive. You just want it to tell information that it has locally and not go asking anybody else about it. So it's a different purpose. And we're going to set up one of these servers, and then we're going to convert it into one of those servers. So you see how they both go. This is an authoritative server, and this is a non-authoritative recursive server. Those are the two types of servers you should have. Yeah, very good. All right. And so large companies, of course, will probably have geolocated services and probably Anycast, many servers all over the place, and a system to redirect traffic from one to another if this whole region goes dark because of like a massive power outage or something. Then this is what big services like the root of DNS and Cloudflare and Google and such use, geo-distributed services. Yeah, what's that?
So those data centers, do they have the same data, copy of the same data?
Yes. That's what you'll have many servers, and they're all going to have copies of the same data, so they can take over for each other. That's what you need for this to work, and that's what the big companies like Google and Yahoo and Cloudflare have. Absolutely. All right, and so you can have a hierarchical structure as well. This is what we have here. You have the internet, then you have caching services at the third layer, second layer, and first layer. This is what we have. So if two people at your company try to go to yahoo.com, they might hit the same server that has it cached, so they don't have to ask any higher. And each one of these only handles one layer. This is what you really have. All right. And I talked about this. This is what Anycast does. You'll have two servers with the same IP address at different geographic locations, so traffic will be automatically routed to the nearest one, but if this one goes down, traffic will be automatically rerouted to another one. That's how you protect something that you really want to stay up. So, I think I got a Kahoot or two about this.
I have a question.
Yeah.
Go back to the other slide. Will it be the delay if the one service falls down?
Absolutely. There will be a delay. You go to the closest one, we'll give you the fastest response. If it's down, then it will take longer to reach the next one. Yep. But typically, the delay is not very big. It's only like 200 milliseconds to go over the ocean. So normally, you won't be too bad. But you're right. It's better to go to the closest one. Absolutely. Which is why, when I use Cloudflare, it means people in Asia get better service because they're looking at a copy of my page that's right near them. They're not all trying to go to my main server. Yeah. Good. These are all very good questions. All right. Let's try the Kahoots. I've got a 2A and 2B. So I should have ran one of them earlier, but I didn't have the slide to remind me where it goes. So we'll do them both at once. the CEO of Cloudflare. He gives talks at me and stuff, and he says he tests the Cloudflare network by disconnecting a whole location, like San Jose. He says if you're pinging something, you will lose one ping. It takes 1 second to redirect all the traffic to another location. All right, so what did we use before DNS? The hosts file, which is still present in modern machines, and you can use it for purposes like blocking spam, but that's what all there was in the early days. All right, which of these is a top-level domain? The last bit, the info, or .com or something like that. All right, which of these is a fully qualified domain name? This is it. The top-level domain is info, the domain is Sam's class, and the www specifies the particular device connected to it, which is called a host. For some reason, every device with an IP address is technically called a host, which is probably kind of a misnomer these days, but it dates from the early days when all those were like shared servers. All right. So which device stores all the DNS records for a zone? The servers have it. The rest of these just ask somebody else. They don't really have it. They're all trying to get eventually to a server where they'll find the information. All right, so if you add a new server, where should you put its DNS record? You do need to put it on a server, but in particular you need to put it on the start of authority server. That's the master copy. That's the one that will be copied to all the others. If you put it on just one of your servers that's not the start of authority, then not all the queries will find it. Only the ones that go to that particular server. So the start of authority, that's what it's for. That's the master copy. Gesundheit? All right, and so what process copies all the records from one server to another? That's a zone transfer. And Microsoft reused this word for replicating a domain controller, which is Microsoft's version of the same thing, although it does a lot more than DNS does. Anyway, that's a zone transfer. All right, Nikki? stated. It might be enough for my grader to uniquely identify you, I'm not sure. Winnie the Pooh will have to tell me real names if they want points. Alright. Good. And I got another one of these. We'll just go into that because I already did the whole chapter. So. Like we got everybody. Okay, which record contains an IP version 4 address? Okay, that's the A record, the most common one. A for address, I suppose. Which record contains the name of a DNS server? NS for name server. All right. All right. What's inadder.arpa for? Reverse DNS, not recursive, but reverse, where you go from an IP address to a domain name. All right, when you opened kahoot.it, what kind of query did your computer send? A recursive query is what you normally do. You ask the router and say, find the answer, even if you have to ask somebody else. Now, an iterative query is the other one, where I'd ask my router, say, only tell me if you know, and if you don't know, I will ask someone else. So I will have to originate multiple requests. Recursive is normally what you want, where you just want the answer and you don't care where it comes from. So where are the glue records? They're on the top-level domains, like .com and .net. Not in the root. All the root has is those 13 addresses of top-level domain. Or 13. All they have is the address of the top-level domain servers, one for each domain name, like .com and .net. which I guess is getting to be quite a lot. In the early days, there were only 7 top-level domains, but now there's a lot more. So I guess the root must have a lot more information in it now. All right. I think that's it. Nope, one more. Okay. Which record is used to stop spam? Email spam in particular. Okay, that's Sender Protection Framework, SPF. All right, I got Charles. And maybe only one Charles. And John again. And Rudy again. Good. All right. All right. Well, we've been here another hour. Let's take a 10-minute break until 10 after 11, and then I'll just demonstrate the projects. It won't take long. I'll stop this recording.